So now that we know the basics of logarithms and logarithmic functions, let's work through some examples. Now these we can do without a calculator, just by knowing what logarithms are. Find log to the base 7 of x when x is 49. In other words, if we put 49 in for x, so we're talking about the base 7 log of 49, what is that? And remember, the log base 7 of 49 means the power that you have to raise 7 to get 49. So when I say, what's the base 7 log of 49? I'm saying 7 to the what power gives you 49? And of course, the answer is 2. 7 to the 2 power is 49. What's log base 13 of x when x is 13? So if we put 13 in here for x, we're talking about the base 13 log of 13. And that means we're asking, what power do you have to raise 13 to end up with 13? 13 to the what power gives you 13? Answer, 1. Okay, what about log base 13 of x when x is 1? That is, 13 to the what power is 1? What's the power you have to raise 13 to end up with 1? Answer, 0. 13 to the 0 power equals 1. Remember how anything to the 0 power is 1? What is log of x when x is 10,000? So if we put 10,000 in for x, and notice there is no little subscript number to tell you what the base of the logarithm is. Remember what that means? It means we're talking about the common or base 10 logarithm. So this is asking 10 to the what power gives you 10,000? What's the power or exponent that you have to raise 10 to end up with 10,000? Answer, 4. 10 to the 4 power is what gets you 10,000. Log of x when x is 0.01 is asking, okay, 10 to the what power is 0.01? Answer, -2. 10 to the -2 power would be 1 over 100, or 0.01. Now here are some that we do need a calculator for. So get your calculator and play along. Punch these into your calculator and make sure you get the same numbers that I do. So the function we're evaluating is log of x. And if x is 86.3, we want the log of 86.3. So you should get 1.936. And then there are more decimal places after that, but to 3 decimal places is 1.936. So that's the power that you would have to raise 10 to end up with 86.3. 10 to the 1.936 power is, well, it didn't come out as exactly 86.3 because it's not exactly 1.936. It's 1.936 with a bunch more digits after it, but pretty close. Now, even without the calculator, I could have told you that the answer was going to be somewhere between 1 and 2. Because I know that 10 to the 1 power would just be 10, and 10 to the 2 power would be 100. So to raise 10 to a power and end up with a number like 86.3 that's between 10 and 100, the exponent would have to be something between 1 and 2. And it turns out that it's 1.936, and so on. Okay, how about the log of 1/16? Try doing that on the calculator. The log of 1 over 16. And with this calculator, as soon as I push the log button, it sticks in parentheses. Some calculators don't do this. So if your calculator didn't put in the parentheses automatically, you're going to have to put parentheses around the 1/16th so that the calculator doesn't think you are asking for the log of 1 and then divide that number by 16. So the correct answer is negative 1.204. That's the power you have to raise 10 to get 1/16th. And now what about negative 13.6? What's the log of negative 13.6? Well, let's see what the calculator says. It says error, non-real answer. Oh yeah, I could have expected that because remember we said the domain of a logarithmic function is all the positive numbers. So you can have the logarithm of any positive number, but you can't take the logarithm of a negative number. So the log of a negative number or the log of 0 would be undefined. It's just not part of the domain of the logarithmic function. Now, back to the calculator, but this time we're evaluating ln of x, the natural logarithm of x. So, of course, we're going to be using the ln button. The ln of 456, the natural logarithm of 456, is about 6.122. So that's the power that you have to raise e to end up with 456. E, that number 2.71828 and so on, to the 6.1224928 and so on power is 456. Okay, how about the ln, the natural logarithm of 0.43? That comes out to negative 0.844 if I want it rounded to 3 decimal places. So to the nearest thousandth, it's negative 0.844. What do you think is going to happen if I ask the calculator for the ln of negative 1.5? Okay, calculator, what's the ln of negative 1.5? Did you see that coming? We got an error message because, again, you can't have logarithms of negative numbers. And how about the ln of e to the 7? Well, let's try that on the calculator. The ln of e to the 7 is 7. Yeah, I was expecting that because remember, ln, the natural logarithm function, is the inverse of the exponential function. ln is undoing what this e here is doing. So ln of e to the anything is just that thing. Now notice that these two expressions are different from one another. The first one is asking for the natural logarithm of the number 4/7. And that comes out to be negative 0.55961, so about negative 0.560. B is asking for the natural logarithm of 4 divided by 7. So first we take the natural logarithm of 4, and then whatever that number is, that number gets divided by 7. And the result is positive 0.198. So it definitely makes a difference. Do we divide first and then take the logarithm, or do we take the logarithm first and then divide? It definitely makes a difference. It's two different things, so be careful about that. And finally, a couple of easy equations to solve. Base 3 log of x plus 1 equals base 3 log of 13. Okay, remember that 1-to-1 property? The only way the base 3 logs of something can be equal is if the somethings are equal. In this case, the x plus 1 and the 13 have to be equal to one another. And then just Subtract 1 on both sides, x equals 12. Another one, ln of x equals ln of 5.2. Well, the only way that can happen is if x equals 5.2. There's no way you can take the ln of anything other than 5.2 and have it be the same as the ln of 5.2. Now later on in an upcoming section, we'll solve some far more complicated equations, but these are really easy ones based on the one-to-one property. So that's it for logarithmic functions. See you next time.